This is a little presentation I've put together for the first part of Chapter 6, Memory and Data Storage. In terms of the IGCSE Computer Science, with the exam board being Cambridge, I am Mr. Bulmer. I'll be your teacher for this. Okay, so the chapter looks at 4 different areas of study, and it starts off, it's quite bizarre, it starts off with file formats, rather than actually starting off with memory storage. But anyway, it obviously it wants you to know about different file formats so you can know what you're storing, I suppose, in primary, secondary, and offline storage, and also how you might compress these files in order to fit more on primary, secondary, and offline storage. It also talks about magnetic and optical media. Both, you'd argue, in most cases are obsolete, but anyway, solid state has taken over. But the book was written in 2015, and a lot has changed since then, as we've found out. Okay, so for this presentation, I'm going to look at these, these 5 areas, jumping the gun with MIDI. We've got MIDI, we've got MP3 and MP4, JPEG, both these two are to do with sound. MIDI and MP3, you may have heard of them. MP4, a little bit more than MP3 in the sense that it's also for multimedia such as video, pictures, etc., things like that. JPEG is basically a universal compressed image format. I will try and talk about a few more image formats. Text and number formats, and lossy and lossless file compression. Okay. I'm using the textbook, I'm using information from the textbook. I hope the publishers or the authors don't mind. I'm using the textbook and the study and revision guide, both written by David Watson and Ellen Williams. This does also link in with the videos on YouTube by Liam McQuay. Fantastic videos. But I don't know whether it's, it means that he's writing for several different exam boards. But this is specific to Cambridge and specific to this chapter, chapter 6. So MIDI files are first in terms of music files, but it's not actually a storage of music. It stands for Musical Instrument Digital Interface, and what that basically means is these files, these .mid files, or sometimes .midi files, what they actually are, it's the files that store notes and store how notes should be played. It looks at the pitch and various other things. But if we look on here, it's giving values of notes, and giving values of chords, various other things, a numeric value. And of course, with that in mind, it means that electronic musical instruments, such as keyboards, synthesizers and things, can talk to each other. They can also talk to the computer. If you've used anything like GarageBand, you might be aware of MIDI files. What you might not be aware of is they operate on 16 channels. The beauty of this is it allows lots of instruments to sort of talk to each other and work together. So you may have seen these mixing desks and things where you can add lots of instruments, ideal for like orchestras or bands, and play them at the same time. Of course, then store them in a MIDI file. They take up very little space. They're very tiny. I mentioned that there. So they are also ideal, and I don't know whether they use them nowadays, but again, one of these back in the day things. They're ideal for ringtones on mobile phones. So that's the MIDI file. They're the advantages of that. Now, unlike the MIDI file, we have another file format called MP3 and MP4. I'll talk more about MP3. MP3 is basically it's the universal format for compression, and it's the thing that's killed off the CD, basically now everything is MP3 format. It's it shrinks a normal sort of music file down by about 90%. It's incredible. So it is deemed, and I'll come onto this a little bit later, it is deemed a lossy compression. Okay, a lossy compression. Now, what that basically means is it removes any, well, you could argue, unnecessary information. It removes sound that the human ear, as I've written there, cannot clearly distinguish. Okay, you may have heard of things, FLAC files and various formats which aren't compressed. Off the top of my head, I can't think of any. The FLAC is the one I'm familiar with, which is again files that fit on a CD, and they are basically 90% bigger than MP3. There's actual size, no compression, therefore there's no loss in anything. But if you can't, I must be honest with you, could you tell the difference? I'm not sure. Now, the difference, as I mentioned before, MP4s can also store multimedia, such as movies, pictures, and, of course, sound. And the format, generally, the file name is .mp3 for a music file and .mp4. But they have taken over, as I say, all the images stored on your mobile phone will be in JPEG format, whereas all the sounds, all the music, will be stored, if it's not streamed from a website, if it's stored, it will be stored as in MP3 format. So, I'm going to go through this with you. This is from the book, from the textbook, and it talks about file storage. So I'm going to try and break this down for you. A CD is used to store some music. Each minute's worth of recording takes up 12 megabytes of space. Okay, the CD contains 9 tracks of different lengths. Yeah, how much memory could these 9 tracks occupy on the CD? That's part A. So you're basically adding all those together and times them by 12 megabytes. If the CD was downloaded to a computer and then all the tracks were put through an MP3 compression algorithm, how much memory would the 9 tracks occupy? Well, it's basically they will occupy 10% of the space if we're assuming that they're compressed by 90%. So you'll see the maths for that in a second. And then finally find the average size of each of the MP3 tracks and then estimate how many megabytes and how many MP3 files could be stored on an 80 megabyte CD. So we need to find the average of those 1, 2, 3, 4, 5, 6, 7, 8, 9 tracks. So let's have a look at the first one. So we've got 9 tracks, yep, and they add up to 48 minutes. Okay, they add up to 48 minutes of music. Okay, so 48 minutes of music, but how many megabytes does that take up? Well, we times 48 by 12 and we get 576 megabytes. That's part A complete. Part B, if the CD was downloaded, as I mentioned earlier, so we've got 12 tracks. Hang on, that's not right, is it? Should have 9 tracks. Sorry, yeah, there we go. What did I say? Sorry, let's go back. 12 tracks equals 557.6 megabytes. Okay, well that's 12. What we don't want 12. If you reduce by 90%, it basically means down to 10%. They would take up 57.6 megabytes. Sorry, that is correct. Let me, yeah, 576, but it's 9 tracks. It's not 12. Yeah, I'm going by the number of megabytes. So that answer remains the same. It's basically that 10% is 57.6. Please ignore my counting. The next one I've corrected myself is 9 tracks, yeah, equals 57.6 megabytes, yeah. We're dividing that by 9 to get the average, which is 6.4 megabytes. Therefore, 800 divided by 6.4 equals 125 music MP3 tracks. Okay, yeah, 9 tracks. Okay, so that would answer, they're the answers to the questions in the book. Okay, JPEG. JPEG. These are the files I talked about which will fit on your mobile phone. In the book, it shows you a picture of a couple of clear wheels on a car, a couple of 5 alloy wheels basically, and the more you zoom in, yeah, the more pixelated it's going to get. So the resolution of photographs is reduced from A to E. Basically, E's become unrecognizable. This results in changing the number of pixels per centimeter. Okay, used to store the image. Okay, so that's it. We're basically reducing the picture resolution. That's what it's saying. Okay, as I said before, JPEG files use a compression system that is lossy, which basically eliminates what the human eye may not necessarily see. Okay, so I think the human eye, I mentioned this before, can see up to about 10 million different colours. Where if you take a photograph on an SLR camera, it can hold up to 30 million. So there's elements that you would never see with the naked eye. But when it comes to resolution, that's when we start to get problems. If we take a JPEG image and want to blow it up, let's say we've got an image that we've photographed the size of a postage stamp, and we want to blow it up to fit on the size of a billboard or the side of a lorry truck, then we're going to lose that quality. What the JPEG file does do, which is a little bit like lossless compression, which I'll come to, is if it takes an image such as this, where you've got lots of blue sky, lots of green grass, basically limited colours, but lots of pixels that are the same, it will try to group them together, and you will get a lot. You'll get a file size that is a lot smaller than an image, let's say, that's very, very complicated. So if we had a sort of a cityscape with lots and lots of different buildings, different colours and things, you would usually find that the image size ran through it, if it was compressed using JPEG formatting, would be bigger than this one. So that's JPEG files. And again, we've got a little problem here. An image which is 1024 wide with by 2048 pixels high would equate to just over 2 million pixels, which is basically equates to 2 megapixels. If this image is fully RGB, red, green, blue, it would need to be multiplied by 3, e.g. 2 megapixels times 3, which would therefore give us 6 megapixels. Okay, 6, yeah. Left uncompressed, it would need to be stored in an uncompressed file, such as a bitmap or TIFF. What I haven't mentioned there is it's 6 megabytes as well. And if I show you on this next one, and we've broken that down here, multiplying it by the colours, we can then say it's basically megabytes. So look at that there, 6 megabytes. So this is the one from the book. An image is 1200 pixels by 1600 pixels, and you will need to calculate several different things. The total number of pixels in the original file. Oh, excuse me. No, I've gone back, I need to go forward. Multiply them together to get the answer there. Times them by 3. Yeah, so 2 megapixels times 3 equals 6 megabytes. Okay, so because we've occupied, each pixel occupies 3 bytes. Yeah, one being red, one being green, one being blue. So there you go, 6 megabytes reduced by a factor of 8, basically divided by 8, and we get 750,000. 1,000 what? Well, okay, 750,000 bytes, but 1 megabyte equals 1,000 bytes, so therefore 750,000 bytes equals 750 kilobytes. Okay, you will need to know about these various, certainly in terms of everything's sort of multiplied up by 1,000. So in terms of bytes to kilobytes to megabytes. So if we go from bytes to kilobytes here, we get 1,000. If we go from so therefore times 1,000 so 1,000 kilobytes equals a megabyte, and everything. So 1,000 megabytes would equal a gigabyte. 1,000 gigabytes should equal a terabyte. 1,000 terabytes, I think, should equal a petabyte. And please correct me there if I'm wrong, but we're going up in thousands. And if the question is such as this, I would argue that you can use thousands because the exam board should accept if you're multiplying by 1,024, the actual, or by 1,000. It should take both. As long as you're sure you're working out, it should not make a difference. Okay, so why is this image fuzzy? Okay, why is it fuzzy when with magnification? Well, I mentioned a little bit about it earlier. How do we overcome this problem? The image has either been taken at a low resolution or it has been compressed using lossy compression, probably in a JPEG format. That's why it's fuzzy. It's low resolution. The image needs either rephotographing at a higher resolution, more megabytes, or more megapixels, or the amount of JPEG compressions needs to be reducing. I put a little bit in here for those who are familiar with photographic retouching. You could put it into Photoshop or something similar, put some filters across it, and you could potentially sharpen the image. Now, how good you would get it, certainly not as good as a photograph that hasn't gone through any kind of compression, but you might be able to tweak it a little bit, so that might be worth mentioning. And finally, from me, this is not in the book, but and quite a few image files aren't in the book. The GIF file. The beauty of the GIF files, and these are associated with most of the memes or the memes you use, on social media and on your mobile phones. The beauty of these files is they can be transparent. As you can see there, it's set against the orange, the banana man, and it can be animated, and we can control whether it loops infinitely, like it's doing now, or we can how many times it repeats. Very, very good file format. There's also things such as PNG files, files from Adobe, which are portable, and they seem to have taken over JPEG images to a large degree on the internet. And the beauty of those is that they can be transparent as well, and they don't tend to they're scalable, so you can zoom in and out with them, and you don't get the loss of quality like you would with a JPEG. But it doesn't mention that, so I'm not going to mention it here. So that's their GIFs. I think it is worth mentioning. Okay, so we move on to the next bit, which is text and numbers. So we can compress these things. We can compress text and numbers in a similar way, but this generally uses the other system of compression, which is called Lossless. So, but first of all, let's have a look at how we can store it. Now, if we're storing text, it's generally stored in ASCII format. Okay, and we've come across ASCII format in a previous chapter. There's a great big table for that. So it basically means that every letter value has given a number. I've shown the numbers here in denary, and again, you stick a percentage sign in front of it if you are using hexadecimal. It gets me that they use a percentage sign for this, but then when they're using hexadecimal in web colors, they use a hashtag. But anyway, that's by the by. So that's how you store text using ASCII format, universal standard. So in terms of storing numbers, and if you've used databases, you've certainly used spreadsheets before. These can be stored in a variety of different ways. A real number, is the one with decimal point. It's also known as a float, and this is where you will get mixed up. I have had many students who have had this in the exam, and it's taught about number formats, and they've written down float. which of course is what it is in Python, but it is deemed a real number in databases and spreadsheets. So if they talk about number formats, you want to think about real. Okay, integers, whole numbers. There we go. Same as Python. Date formatting. Yeah, usually the day, the month, and the year. Time, the hours, the minutes, and the seconds. And it can be broken down even further. And currency, whatever the denomination is, whatever the currency is for whichever country, and then usually with a decimal point in between. Usually no more than 2 decimal places for the number of, such as pence if it was pounds, or cents if it was euros. So, compressing text files. As I said before, we're going to be using lossless compression. It can be compressed, and it involves various algorithms, but the algorithms look at repetition in parts of the word or in full words in a phrase in a sentence. So I've got a sentence here. Again, this is from the book. This section shows you how this would work. The sentence, contains 35 letters, and you can count them, but ignoring the spaces, okay? It's also known, rather than letters, memory units, and this will become clear in a moment, So 35 letters. But how do we compress that? If we go to this, okay, this section shows you how it's the sentence again. I've looked at the sentence, and I can see that I can split it because the word this repeats. The word how, or how, is there, but it also appears in shows, so that appears twice, and then the O and the U in you and in would appears. So I can give these numbers and give these numerical values. So I've given this number 1, how number 2, and OU number 3. Okay, so now we can rewrite this sentence, and it stores it as only 23 units. And there we go, we've reduced it by 33%. Okay, a little challenge for you there. We've got another sentence: compare text files in a computer after file compression. Okay, so that is one for you to have a little go at. So I'll just go back before I do a summary of this this part unit. So yeah, please either pause the video or but basically have a little go based on the previous slide. Have a little go and see if you can get that reduced down by 40%. Some things are fairly obvious in there, but I'll let you have a little look. Finally, these are the 2 types of compression. Why are there these 2 types? Well, I'm going to try and explain it to you. Lossy, we said it eliminates unnecessary information. It's when some of the original file is lost. It can't be got back. You can't retrieve it. It is gone. You compress it. You cannot retrieve it. Okay, it's lossy. Using images in JPEG format and multimedia MP3 and MP4, as I mentioned earlier. Now, the differences with that and lossless is all the data in the file, when it is uncompressed, it's retrieved and it comes back to its original format. It's essential in such files as text files, spreadsheets, database, and programming code. If you had the full works of Shakespeare or Dante, and you tried to retrieve it and there was letters missing or it was jiggled about, there was something not quite right with it, it potentially could be illegible. And it would be the same for the spreadsheet if you imagine some of the macros had gone wrong or the data itself had changed. Then things would not add up, and that's the same in the database. And of course, finally, if you had a great big piece of Python code, and you compressed it using Lossy, and you lost elements of the code, you can guarantee you would end up with syntax errors and all various other things. So lossless, yeah, it's imperative, but and it looks at number patterns or letter patterns. It will uncompress to its original format. So that's basically the difference, which takes me nicely on, and I recommend Liam McQuay's video on looking at memory, looking at RAM and ROM. I may do a video which sort of supports that. But until then, thank you very much indeed. Please have a little go at the questions if you've not done so already. Thank you very much, and I will see you next time.